Welcome to part 2 of the buggy creation using Flowcode 6. In this video we're going to look at adding a bit of rotation and maybe adding the embedded side code to drive some actual motors. So first let's try and add a new macro to allow us to turn the buggy. For now, to keep things simple, I'm just going to use a spin on the spot. So I've got a spin left, the robot to the left. I'm going to put a speed in here so we can vary how fast the robot turns. Spin left, and in here we'll copy our speed variables. As we're spinning to the left wants to be negative to go backwards, the right wants to be positive. Then if we right click the spin left macro and duplicate, we can create spin right. Spins the robot to the right at given speed. As we're going to the right, the left wants to be positive, the right wants to be negative. Okay, so in our main loop, instead of going forwards and backwards, let's change things up a bit. So it goes forwards for 2 seconds, spins right, speed 100 for 1 second, and then goes forward again. So in our EV timer macro, here we have if speed left is equal to speed right. So that's if it's going forwards or backwards or stopped. So instead, now we're rotating, the speed left is not going to be equal to speed right, so we'll come down this branch for the decision. So again, we want to stop any animation. In fact, it might be a good idea to move the stop animate out of the decision, and also the animate out of the decision. And that way these two will always fire, and it's just these things that will change. Even the get position can be moved out. So if the speed is equal, then we'll move. If it's not equal, then we'll rotate. So instead of move by, we'll use rotate Z. The handle is our position handle. The pivot handle is also the position handle, i.e. we want to pivot around itself. We don't want to pivot around another external object. The degrees, we set this to speed left. Actually, let's carry on setting it to flow at speed left with the divider. So we save that, and then if we run this, let's see what it does. So it's rotating the object, but then it's carrying on moving in the same direction. To fix this, we can simply change the move by to move along, and this provides an extra axis. So if we use the handle as dot position, the axis as dot position, and then use the same movement in the y-axis, and this should then use the local axis of the object rather than the panel axis. So let's see what that does. Okay, so we've got a little program that will allow us to drive the robot around, turn on the spot, and it all simulates quite well. Let's say we wanted to actually drive some hardware with this. One way would be to use PWM, pulse width modulation, and you would use two of these. So I'll just dump these on my simulation panel, and then I'll stick them onto my dashboard panel just so I can see them a bit easier. So, if I name one of them left and the other one right, that helps to identify which is which. Under properties, left is channel 1, right is channel 2, so they're both using hardware PWM. Then in my Project Explorer, I'll make a new macro which is set PWM, and this has two parameters. Which is left speed int. Actually, these are globals anyway, so I'll just get rid of them as parameters. We just have a set PWM, and this will update the PWM outputs based on our global speed variables. Set PWM. If speed left is less than 0, the way the PWM works is it gives you a mark space ratio on the square wave that's being output. You can use the PWM along with an output pin to then be able to control the speed and direction of the motor. So if we create two properties, so if we say left motor direction, and the variable can be left motor, we'll choose a single digital pin, we'll duplicate that, and this is now the right motor direction pin, right motor. So speed left is less than 0. If it is, then we want to set the left motor direction pin, so equals 1. Otherwise, we want to go forwards, so forwards, backwards. We'll do the same for speed right. So this time, right motor dir is 1 and 0. So this sets the pin states for our sort of bridge to drive the motor. Next we need to set the PWM period. So if we go to our set to PWM macro, and we create a new sort of local variable, and we'll call this speed. If the left motor is greater than 0, then dot speed is equal to speed left. If speed left is less than 0, then speed is equal to 255 plus speed left. Speed left's a negative number, so we should get 255 being fully off, and as the speed increases negatively, this speed will also increase or decrease in terms of mark space ratio. So we'll do the same thing down here. Speed equals speed right. Speed equals 255 plus speed right. And then we need to call the PWM component. So this is left, set duty cycle, and this is dot speed. And then again, after the right decision, we have right set duty cycle speed. Then in the main, we need to enable both the left and the right PWM so that they're active. So they're both enabled. And then we also need, in all of these movement macros, we just need a reference to our new set PWM macro. And that will allow the hardware to always be doing whatever the variables are doing. Okay. So now if I scale this up a bit, let's give this a closer look. Set this running. It's warning me that these pins aren't connected, but that shouldn't matter too much for the simulation. See, the PWM is now reacting to how the motor should be working. If we want, we can also use outputs, LEDs, and just use these to view the state of the I/O pins. So if we say this is connected to A0, this is connected to A1, and then our actual component pins, we connect them to the same values. We should then be able to see the left motor coming on when it turns. So there we go. So there we've added some on-the-spot rotation, and also we've added code that will allow this to actually work on physical hardware. As opposed to PWM components, you could use servo motors and mod the inner workings of the servo so it provides constant rotation rather than positional control. That's very good for a motor drive for a buggy, but I'm going to keep my example for PWM for the rest of these series. Many thanks for watching, and I hope you join me for part 3.